All right, everybody, I'm on page 58 of your unit packet, going over the key levers for applications of integration. This first key lever doesn't have a model problem associated with it. It's just the big idea that a definite integral represents area under a curve. So this is a great visual to help you understand that anytime you've got a region that's bounded on the x-axis by a and b, that function creates a nice two-dimensional surface here that I can calculate the area of by utilizing the definite integral. So this integral is always representing area bounded by a function on a given window, in this case from A to B. So very important key lever that we'll see all over our AP exam. The second key lever is approximating with Riemann sums. So this is an excellent example to highlight some big ideas behind Riemann sums. We have a continuous function on the interval 2 to 8, and some values are provided to us here in this table. We want to use the given subintervals to determine the trapezoidal approximation of the definite integral from 2 to 8 of f of x. So this is great because a lot of you always feel the need to use the b minus a over n formula anytime you see that you're in a Riemann sum problem, but this only applies when you have equal widths provided or equal widths indicated in the stem of the problem. Nowhere in this question do I see anything about the intervals being equal or the widths being consistent. Nowhere do they indicate that in this question, and in fact they actually go so far as to tell us the intervals to consider, and upon inspection those are not equal width at all. So we have to be really careful about that. Y'all always fall for that one. So don't forget that trapezoids are equal to the average of our left and right hand Riemann sums. So if we keep this in mind, we can pretty nicely indicate the approximation being requested here. So my approximation is going to be the left-hand Riemann sum, the right-hand Riemann sum added together and divided by 2. So when I look at this first interval, the distance between my x's is 3, and the output on the left-hand side is 10. That's my first rectangle. Plus, as I keep going, the distance between the next two x values is 2. The output on the left side, I can annotate those, is 30. And I'll do one more. The distance between the last two inputs is 1. And the output on the left side is 40. I do some quick math. That's 30 plus 60 plus 40. I think that's 130. And y'all can check me on a calculator. I do my right-hand Riemann sum. Let me go ahead and switch colors here. So the distance between the first two x values is still 3. But now I'll choose the value on the right-hand side. That's 30. Next still has a width of 2, but the right-hand endpoint is now 40. And then finally we have our width of 1, and on the right-hand side we grab the output of 20. I do some math here, and I believe that I get 90 plus 80 plus 20, 190. So what I'm able to conclude based on all of this is that the integral from 2 to 8 of this function is approximately equal to the average of those two summations. So 130 plus 190 over 2, which if I do some thinking, hold on, I'm too tired to do mental math right now. I'm pulling up a calculator on my phone real quick. 130 plus 190 over 2, 160. I should have known that. Sorry, y'all. And there we go. I've got my trapezoidal approximation. Our third key lever involves integration properties. College Board loves to assess this, and it's a pretty straightforward concept if you can remember a few things. So I'm given the value of the definite integral from 2 to 4 of f equal to 6, and I'm asked to evaluate the integral from 2 to 4 of f of x plus 3. So one of the properties of integrals that's really helpful here is to remember that if I have the integral bounded by 2 and 4 of f of x plus 3, I can easily split that into two integrals with that summation in the middle. That's a really helpful rewrite here, because this first one, the integral from 2 to 4 of f, that's given to me in the problem, that's 6. And the second integral over here is actually not horrible. I'm going to show you how to do this in 2 ways, and you can decide which one you like. The analytical approach is to ask yourself what the antiderivative of 3 is, and the antiderivative of 3 is 3x, and I want to run that from 2 to 4. So I plug the 4 in first. That's 3 times 4 minus 3 times 2. That's 12 minus 6, or 6. That's one way to get the 6 down here. Option 2 is to think about this graphically. The function 3 is a horizontal line at y equals 3. And I want to find the area under that from 2 to 4. So that region that I see right here is just a rectangle with a base of 2 and a height of 3 and an area then of length times width, or 6. So analytical approach or graphical approach, either option gets me to my final answer of 12. Okay, key lever number 4 is big. It's the fundamental theorem of calculus. I didn't snip the whole theorem over here, but it's there for you on page 59 in really technical language. What I want you to remember all the time when we're dealing with the fundamental theorem of calculus is that new equals old plus change idea. Anytime you recognize you're being asked for something new, or that you've been given something old, you can always try and link up with this formula to help you out. So what I'm drawn to when I read through this model problem is this definite integral is given to me right here, and I'm remembering that a change is always represented by a definite integral. And then I can continue reading and I realize, hey, I'm being asked for f of 4. That looks like a new value when I see this integral right next to me over here. The new value is always the upper bound. So if I want to work through this new equals old plus change idea, that means f of 4 is going to equal my old value f of 0 plus the change that occurs from 0 to 4 of that next function, in this case f prime of t dt. And in this problem, this is a really nice application because I just have to go hunt in the question to find everything that I need. F of 0 is looking at me right here in my table, that's 5. And the value of the definite integral was a given. They told me that that was 8. So my answer on this new equals old plus change question is 13. So key lever number 5 is average value. That's another common application of integration that we'll see. The theorem is here for you. Average value is the integral from a to b of a function divided by b minus a. This format shows that multiplication of the reciprocal out front, but those mean the same thing. So in this model problem, we've got air pollution measured here with respect to miles, and that's described by L of x. We're asked to find the average level of pollution between 15 and 25 miles from the factory. So when I read this, my window that's being requested is 15 to 25. So if I just plug in here, my average value states that I'll take the reciprocal of those endpoints and multiply by the integral from 15 to 25 of L of x, which is e to the negative 0.1x plus 1 over x squared. And if you just toggle over to a calculator, you can do this. So I'll divide 1 over 25 minus 15. I'm not going to do any simplifying myself. I'm going to let the calculator do it. And then the integral is from, 15 to 25 of that function, which was e to the negative 0.1x plus or minus, I don't remember, let me go look, plus 1 over x squared. So I just type the rest of that function in, put my dx on the end of my integral, and my average value is 0.1437, which I can then record and be done. All right, on to key lever number 6. This function is defined by integrals. Another common name for this is the second fundamental theorem of calculus, where you have a function that is equal to a definite integral, and you're asked to take that function's derivative. So the rule is right here. Anytime you see the derivative of an integral, those two operations right next to each other, we're able to apply this kind of variation of the chain rule and take the function that was inside that integral, evaluate it at the upper bound function, and then multiply out by the derivative. So here's a perfect example of this. I see a derivative and an integral right next to each other, constant on the bottom bound and a function on the upper bound. So just straightforward application of this rule results in the square root of 1 plus, not t squared anymore. I'm supposed to take that entire function that I see here, and instead of evaluating at t, evaluate at the upper bound, which in this case is x squared, and then multiply by the derivative of that upper bound, which is 2x. So the only real thing I can do here to maybe simplify this out a little bit is pull the 2x in front of the square root and put a 1 plus x to the 4 in there, because that's what x squared is. Okay, and my last key lever here involves rate functions. So very, very common application of calculus is to be given a rate of a given quantity and be asked to analyze that rate. In this example, we've got a cup of coffee that is originally 90 degrees Celsius put into a room temperature room. The coffee's temperature is changing at a rate, that's a very important word, given by that function. Find the temperature of the coffee at 6 minutes. So what I'm really drawn to here is that R of t is being measured in degrees Celsius per minute. That's a rate function. So if I think about stairs, this question asked me to actually find the temperature of the coffee. So a degree Celsius is being requested. And the only way to get from degrees Celsius per minute to degrees Celsius is to go up the staircase. So a degree Celsius is going to be up here where big R is living. And we know enough about this to understand that moving up a stair requires an integral. So this is actually going to combine a previous key lever in the context of this rate situation, because I'm also asked to find the temperature specifically at t equals 6. So another way to annotate here is I'm really requesting this new value. What is big R of 6? Well, big R of 6 is equal to old plus change. So that's going to be my initial temperature at 0 plus the integral from 0 to 6, from old to new, of this rate function, which is negative 7e to the negative 0.1 t dt. I can plug in, my coffee was originally 90 degrees Celsius, and now I'm adding the change into this situation. And what I would do is just type this whole thing on my calculator all in one line. That's going to be 90 plus my change, which we say is the integral from 0 to 6 of, if I get this right, negative 7e to the negative 0.1 t, x, whatever variable you want, your calculator will understand as long as they match here. And my temperature of coffee is now 58.4168 degrees. Let's go record that. And we've got our final answer. That's the last key lever here. I'm so shocked I got all of them into one video. But your job now is to go back to your packet. Here's mine. We just did key lever number 7 on page 60. The check my understanding that you're going to be responsible for scoring with each other tomorrow is here on page 61. You're going to want to try and earn as many points as you can on parts A through E. And everything should be pretty straightforward with maybe the exception of part E. But everything else you've seen before and you have notes to help you with. So go ahead and take care of that and we will score it tomorrow. Thanks, guys.